Okay, 1.5 properties of limits. So the statement, the limit of f at x as x approaches a equals L, says that the values of f at x become closer and closer to the number L as x gets closer and closer to the number a, such that x does not equal a, right? So this is where yesterday we don't really care about what's going on right at that value. We care about what's going on just to the left of it and then just to the right of it. Okay, so this means that when finding the limit of f at x as x approaches a, there is no need to consider the point right at x equals a. F at a does not even need to be defined. Okay, so there could be a hole there, and that's okay. The only thing that matters is the behavior of f at x near x at a. So we could have a hole, we can be coming from the left, coming from the right, right, going into that hole, and it doesn't matter that that hole is not filled in. We only care what is happening approaching it for that point from the left and the right. Is it approaching the same number? Okay, so today we're going to look at properties of limits. This is going to be more of an algebraic approach. So for any real number a, suppose that f and g both have limits that exist at x equals a. Okay, so we're going to consider two different functions. We're going to consider basically f at x and g at x. Okay, so f and g both have limits. So this is only if the limit exists. So the limit of a constant is that constant. Okay, and these are all quoted as the limit as x approaches a. Okay, so as we get closer and closer to the constant, our constant is our limit. Now, the limit as x approaches a of x is a. It's kind of like if we subbed in a to x, that's what we'd get. Okay, now, limits of two separate functions, if they're added or subtracted, what we do is we find the limit of one function, and then we add or subtract, whatever that sign was, the limit of the second function. So what happens is we can take two functions and we can find the limit of each individual component or each individual function and then add them afterward. Okay, 4. If we have some function that's multiplied by a c value, like a constant value, what we can do is we can pull that constant out, find the limit of the function, and then multiply it by the constant. Okay, 5, if we have two functions that are multiplied by one another, what we can do, and like these three are very similar, especially 3 and 5. What we can do is we can find the limit of f at x, the limit of g at x, and then we can multiply them. So we can find the limit of its components again. Same thing goes for 6. This is very similar. If we have the limit as x approaches a of a function divided by a function, so this is rational, what we can do is we can find the limit of the numerator function and then divide it by the limit of the denominator function. So again, these limits, we can consider the numerator of function, the denominator separately, and then divide. So we're looking at the limit of the components of this. And then, of course, the limit of the denominator cannot equal 0. Right? You can't divide by 0. Okay, I'm going to do this in another color. It was difficult to see. So if we have the limit as x approaches a of some function raised to the exponent n, what we can do is we can find the limit of that function and raise that limit to the exponent n. And that's for any rational number n. Okay. So let's take a look algebraically how we can solve for limits. So here's a note. Limits can be solved by using direct substitution. So what we would do is substitute in the number that x approaches, and it will yield the limit of the function. So if you guys think about what this is actually doing, if we're subbing in, for example, example 1, evaluate the limit as x approaches 2 of this function. If we're subbing in 2 to these x values here, essentially we are solving for an ordered pair, basically. Okay, and this works in this case because it's not a piecewise function, it's not discontinuous, this is just simply a polynomial. So if you are able to sub in x approaches 2, if you're able to sub in this 2 to the x values and yield a number, then substitution, direct substitution works. Okay, so let's take a look at what that looks like. Okay, so we have 3x squared plus 4x minus 1. So as soon as we sub in the 2, we no longer have to write the limit. So we can write 3(2) squared plus 4(2) minus 1. This is 4. So this is 12 plus 8 minus 1. So this is 19. So the limit as x approaches 2 of this function is 19. Example 2, evaluate the limit as x approaches 1 of this function here. So we have x squared minus 5x plus 2 in the numerator. So go ahead and sub in 1 to where the x values are. And then in the denominator, we have 2x cubed plus 3x plus 1. Okay, and remember, if this yields a 0 over a 0 or infinity over infinity, which it won't in this case because x doesn't approach infinity, but if it yields a 0 over 0, we cannot have that and we have to think of another method. Okay, so we have 1 minus 5 plus 2 over 2 plus 3 plus 1. We get negative 4, so negative 2 over 3, 4, 5, 6, 6. I get negative 1 over 3. So again, since we can sub in this 1 here to all these x values, we can use direct substitution, and the limit of this function here as x approaches 1 is negative 1 over 3. Example 3, evaluate the limit as x approaches 5 of this function here. So we have big square root x squared in the numerator, so 5 squared, over 5 minus 1 in the denominator. We have the root of 25 over 4. If you think about what this actually means, it means root 25 over root 4, right? So we're rooting both of these components, and we get 5 over 4. Okay, so for all 3 of these, and we looked at 3 different functions. We looked at the polynomial function. We looked at the rational, which is a fraction. And then we just looked at the radical function, which is a square root function, right? So for all of these, if we're able to substitute in directly and it yields a number, then that works. Now, that's not always going to be the case. It's likely not going to be the case. So let's take a look at what else we can do. Okay? So sometimes the limit of f at x as x approaches a cannot be found by direct substitution. And we're left with the indeterminate form 0 over 0. Obviously, this would come from a rational function, right? 0 over 0, we'd have to have a denominator. And at this point, we look for an equivalent function to use. So, example 4, evaluate the limit as x approaches 3 of x squared minus 2x minus 3 over x minus 3. So if we can say try direct substitution. Okay, that's what we're going to try first. So we are going to get 3 squared minus 2 times 3 minus 3 over 3 minus 3. So we're going to get 9 minus 6 minus 3 over 0, which is going to give 0 over 0. Okay? This is not the limit. You cannot put this as your answer. This is indeterminate form. Indeterminate form. So what that means is that we cannot use direct substitution. We have to use another approach. So therefore cannot use direct substitution. Okay, so here's a little bit of a hint. So try factoring both the numerator and denominator and then canceling out. Then substitute directly into the equivalent function. So let's bring this down here. We rewrite the limit because we're not subbing in yet. So let's factor the numerator. What two numbers multiply to -3 and add to -2? I get -3 and 1. So the numerator is going to be x minus 3, x plus 1. And the denominator is just a binomial, so we'll just leave it as x minus 3. Okay, the reason why we got 0 over 0 is because we can cancel out this x minus 3. So essentially, there is a hole at x equals 3, if you think about it. So yeah, you're not going to be able to directly substitute in because it's never going to yield an x comma y like an ordered pair. So now our equivalent function is actually just x plus 1, which is linear. Linear is a polynomial. So now we can do direct substitution. So 3 plus 1, which is 4. So our limit as x approaches 3 of this rational function is 4. Okay, and just up here, root 4 is 2. I'm just going to add a domain. So x cannot equal 3 because there's the hole. Now, here's another approach. When working with radicals, it is common that we must multiply both the numerator and denominator by the conjugate to rationalize the function. Okay, so expand and simplify, and then we use direct substitution. So if we did direct substitution, so let's go try direct substitution. Okay, if we did that, we would get 0 plus 1, root 0 plus 1 minus 1 over 0. So we'd get 1 minus 1 over 0, which is 0 over 0. Okay, so in other words, if you're in a test and you're getting 0 over 0, you cannot use direct substitution. Okay. So what we're going to do is we're going to rewrite the limit as x approaches 0, and I'm going to rewrite the function as it is, root x plus 1 minus 1 over x. Now, let's use the conjugate. So let's multiply by the binomial x plus 1 minus 1, or sorry, plus 1, over x plus 1 plus 1, right? By multiplying by the conjugate, this is also just thought of as multiplying by 1. We're just making our function look a little bit different. Okay? So the limit as x approaches 0, we're going to expand the numerator. So root x plus 1 times root x plus 1 is just going to give us x plus 1. The middle two terms are going to cancel out. I'm not even going to write them anymore. And then -1 times 1 is minus 1. And I'm going to rewrite the denominator as x times x plus 1 plus 1. keep this in brackets, okay? Because this is a binomial. So at this point in time, we can see that in the numerator, we have +1, -1, so those are going to cancel out. And then at this point, we have x over x and then this bracket. The x's also cancel out, leaving 1 in the numerator. So we have, and I'm going to rewrite this just so that it's very clear. We have 1 over root x plus 1 plus 1. Now let's go ahead and try to sub in the 0. So since we're subbing in the 0, we no longer have to write the limit. So we're 1 over 0 plus 1 plus 1. This is just 1. I get 1 over 2. Okay. So to find the limit of a simpler function, what we do is we use substitution. Okay, so I'm going to actually skip these for 1 second. Let's take a look at example 6. So evaluate the limit as x approaches 0 of this function. Okay, x plus 8 to the 1/3 minus 2 over x. If we tried using direct substitution, I'm just going to put ds, we would get 0 plus 8 to the 1/3 minus 2 over 0. Well, the cube root of 8 is 2, so 2 minus 2 over 0. We would get 0 over 0. So we can't use direct substitution with this. However, if I take a look at this part of the function is really ugly. So the x plus 8 to the 1/3. So what we do in scenarios like this is we use something called substitution. So what we'll do is, number 1, we create a let, kind of like a let statement to equate part of the equation to u. So we're going to do let u equals, and it's going to equal this entire bracket. So x plus 8 to the 1/3. Okay. And so that's number 1. Number 2, we're going to redefine the number as u approaches. So what we want to do is we want to isolate for x. Okay, so if we have x plus 8 to the exponent 1/3, what we want to do is we want to raise both sides to a value where 1/3 times that value is going to equal 1. So what we do is we raise it to the reciprocal. So 3 or 3 over 1, right? So we're going to get u cubed. Okay, so u cubed equals, so if you remember power to a power rule, these two are going to cancel. And we're going to be left with x plus 8 on this side. Then what we do is we just bring this over, and we have u cubed equals, nope, u cubed minus 8 equals x. All right, so when we talk about redefining the number as u approaches, so we have in the original question the limit as x approaches 0. But if we're going to change our equation so that we're no longer dealing with an x, what we have to do is we have to sub in this 0 to the x value, and we have to think to ourselves, okay, what does u approach? So if we have u cubed minus 8 equals 0, we bring over the 8, u cubed equals 8, and then we're going to cube root both sides, and we get u equals 2. So what we can do now is we can rewrite the equation. We're going to write it as the limit as u approaches 2, because that's what u is approaching now. And then we are going to substitute in for the x plus 8 to the 1/3. We're going to sub in u. And then we're going to complete the rest of the equation. So minus 2. And then in the denominator, we have an x. So we can't substitute in u again because u doesn't equal x. U equals x plus 8 to the 1/3. But we already isolated. So that was our work when we isolated. So the denominator is going to be u cubed minus 8. And that's going to be our new limit. So going back up here, we redefined the number as u approaches. So that's good. We substituted in expressions with u into all of the x's in the equation. So now there's no x's left. We substituted u in here, here, and here. Okay? Now we solve for the limit. So if we were to sub in 2, we again get 0 over 0. So we can't substitute in yet. We're going to have to factor. So I'm going to leave u minus 2 in the numerator. And taking a look at the denominator, this is difference of cubes. So I get u minus 2, u squared minus 2u, that's plus 2u, and then plus 2. And at this point, I can cancel out the u minus 2's, and we are left with 1 over u squared plus 2u plus 2. Sorry, this is 4 because it's 2 squared. Thank you. Okay, and now at this point, we have a 1 in the numerator, so we know that we're not going to get 0 over 0. So let's go ahead and sub in the 2. And remember, as soon as you sub in, you can drop the limit. Okay, so 2 squared plus 2 plus 4, and I get 1 over 4 plus 4 plus 4, which is 1 over 12. Okay, so for the absolute value function, consider both equations of the piecewise function. So as a review, if we have f at x equals the absolute value of x, what this actually is the piecewise function, okay? And we're going to take x when x is greater than or equal to 0, and we're going to take negative x if x is less than 0. And all that's really going to do is make everything positive. Make positive. Okay, so this is technically the piecewise function. So because the absolute value of x minus 2 is a piecewise function, we have to consider both the positive and the negative pieces of it. So f at x equals, and we're going to have two different functions here. We're going to have x minus 2 over x minus 2. And then what we're going to have is minus x minus 2 over x minus 2. And this is going to be if x is greater than or equal to 2. And this is going to be if x is less than 2 on those two domains. Okay. All right, let's take the first one here. So when we're dealing with f at x equals x minus 2 over x minus 2, if you think about this, these binomials are the same. They can cancel out. And when they cancel out, we get the answer of 1. Okay, now let's take the second part of this piecewise function. Negative x minus 2 over x minus 2. We can bracket the binomials. Okay, go ahead and cancel them out. And for our solution, we get negative 1. Do this with another color. So if we consider what this function actually looks like, okay, at the point 2, comma 1, right? Because even though we didn't actually sub in x approaches 2, what we're doing is we're essentially canceling these out. So then we're finding the limit as x approaches 2, but of a constant now, which is just the constant. So this is going to yield the point essentially 2, 1, and this is going to be 2, -1. So 2, 1 is going to be, so this graph is going to come out of here and go to the right. We can circle that in. And then 2, -1, the graph is going to come out of here and go to the left somehow. And because these 2 points, let's say because this graph doesn't approach the same point from the left and the right, so we can say the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. The limit as x approaches 2 in general does not exist. And I'm going to put the limit of f of x. I'm going to put f of x in here for better form. Okay, example 8. A. Evaluate the limit as x approaches 3 from the left of 9 minus x squared. So the root of 9 minus x squared is going to be half a circle between the numbers -3 and 3. So if we're assessing the limit as x approaches 3, so this is x value, this is 3, as we come in to the 3, what happens is we're not actually coming in from this way. So because we're only coming in from the one way, the limit actually does not exist. Okay? Or sorry, no, the limit as x approaches 3 from the negative side does exist. It is going to be 0 because the general limit as x approaches 3 is not going to exist, but because we're just considering the one-sided limit, it does exist. So let's talk about B. Explain why the limit as x approaches 3 from the positive side cannot be determined. Okay, so there's no function here. That's why. So we can say the limit as x approaches 3 from the positive side of this function f of x cannot be determined because this graph, so f of x, the graph, is not defined on like 3 to infinity. Okay, it's not defined on that domain. Now, what can you conclude about the limit as x approaches 3 of root 9 minus x squared? Okay, so we can simply conclude the limit as x approaches 3 of this function does not exist since the limit as x approaches 3 from the left side of the function will not equal the limit as x approaches 3 from the right side of this function. Okay, because that limit's not defined on both sides. It's only defined on one. And I keep coming back to this because this is the definition of what a limit is.